Assalamu alaikum. I am Muhammad Farghali. Welcome to a new episode of a Paper in 10 Minutes series, visualized by 4D Geosteering.
In this groundbreaking exploration of horizontal well drilling, we uncover the revolutionary study titled A New Method for Predicting Formation Lithology while Drilling at Horizontal Well Bit, authored by Jian Sun, Mingkang Chen, Kai Lai, Long Ren, Menjuan Du, and Jixuan Zhang. Over the course of 2 episodes, we delve into this study to reshape the landscape of lithology prediction in horizontal drilling by integrating machine learning and LWD data. We all know geosteering is a crucial technology in horizontal well drilling, relies on real-time adjustments to well trajectory using geological and LWD data. Despite LWD's long-standing presence since the 1990s, a persistent challenge is the zero length, which is the gap of 6 to 10 meters between the LWD tool and the well bit. This gap delays implementing geosteering decisions as real-time information is collected at the LWD tool, not directly at the bit. So, accurately predicting lithology at the bit remains difficult. Here we go, delving into the LWD history to trace the lineage of advancements. In 1998, Douglas pioneered the use of MWD data for real-time formation dip prediction to prevent drilling outside the formation boundary. In 2004, the introduction of an ultra-deep resistivity LWD tool to detect reservoirs by identification of fluid contacts and lithological characteristics. Concurrently, Roller applied imaging logging technology to analyze formation characteristics, providing accurate borehole positioning within the reservoir. Liu developed a mapping method by integrating LWD interpretation with formation analysis and wellbore trajectory descriptions to visualize the relative position between the current well trajectory and the reservoir. In 2010, Kamali introduced the concept of the geographic signal, a horizontal electrical signal utilized for measuring azimuth resistivity, for ensuring the trajectory stayed within the reservoir. In 2012, Pitcher's proposal for novel sonic logging technique utilizing changes in drilling speed data to determine the distance between the wellbore boundaries to improve geosteering accuracy. Concurrently, Lai established a physical and mathematical model of probing and ranging to determine this distance between the drilling tool and the reservoir boundary in horizontal well drilling with high accuracy, minimizing error rates to less than 5%. Yang proposed a fast-forward method of azimuth gamma LWD and carried out the inverse calculation of the distance between the bit reservoir interface. He used wavelet transform and beta distribution to automatically identify formation boundaries and accumulation patterns in logging. The above studies can be categorized into 2 methods to predict the formation lithology at bit. One is to invert the log curve and then forward it to predict the logging information at the bit. The other is to predict the distance between the wellbore and reservoir boundary by using LWD data and engineering parameters. Logging interpretation is fundamentally a classification problem, seeking correlations between logging feature parameters and interpretation targets. With advancements of artificial intelligence and data mining, these problems become manageable. In lithology identification, scholars have explored machine learning algorithms, including artificial neural networks and support vector machines. This paper focuses on predicting the distance between the wellbore and reservoir boundary using LWD data and SVM algorithms for enhanced recognition accuracy. The proposed method aims to utilize LWD data with integration of geometric mathematics and initial reservoir understanding to establish the relationship between D-MP-VRB, which is the measurement point and vertical reservoir boundary distances, and the lithology identification at the drill bit to overcome zero-length challenge, which cause delays in geosteering. In methodology, beginning with the establishment of database of distance between measurement point and vertical reservoir boundary by utilizing logging data for the target layer in the study area and identifying reservoir boundaries based on lithological interpretations and defining dual distances from upper and lower boundaries, assuming horizontal continuity and low vertical complexity of rock properties, and categorizing various sandstone types into a unified category termed sandstone. So finally, the sandstone reservoir D-MP-VRB database was constructed. The shape of the well log changes obviously with the change in lithology. When the log is far from the lithological boundary, the curved shape of each measurement point in the reservoir remains basically unchanged. But there is a change in the well log near the lithology boundary, and this part of the data will affect the establishment of the D-MP-VRB model. The collected D-MP-VRB data are categorized based on different values, aiming for a balance between granularity and practical applicability. Division that is too fine may reduce prediction accuracy due to small differences between adjacent categories, while overly wide division renders the data impractical. Therefore, selection of appropriate distances is crucial, with intervals of 0.25 meters, 0.5 meters, 1 meter, and 2 meters from the vertical boundary of the reservoir considered. This study operates under several key assumptions to ensure the reliability and applicability of the proposed methodology. The first assumption assumes a continuous stratum without lithological changes horizontally. So, this approach is not suitable for strata with discontinuities and fault structures. The second one is to declare the distribution of sample quantities for each lithology shows minimal differences to prevent weakening the generalization ability of the prediction model and the risk of overfitting. The third one to assure that logging data used for building the model are considered accurate and reliable. The D-MP-VRB prediction model is developed through continuous learning and training on the logging data stored in the database. Here we go to know the scope of application. The D-MP-VRB prediction model can only predict the site with a relatively small distance, in Figure A, where the sandstone reservoir is thick. If the distance between the LWD2 and the upper reservoir boundary, which is H1, is less than the distance to the lower boundary, which is H2, the method can only predict the distance to the upper boundary, which may not be necessary if already drilled. Conversely, if H1 is greater than H2, the method can predict H2, but the zero-length distance may make accurate prediction challenging. In Figure B, where thin sandstone reservoirs appear, regardless of the distances H1 and H2. If the drill bit has already drilled out the sandstone reservoir, the model becomes inapplicable. This situation is common due to the presence of interlayers, rendering the model unsuitable for vertical wells. In horizontal wells within a sandstone reservoir, when H1 is less than H2, the D-MP-VRB model can predict H1. Subsequently, the prediction formula for the distance between the bit and the reservoir boundary can be derived, allowing calculation of H3 to determine the lithology at the bit. Therefore, the model proves suitable for horizontal wells. The maximum distance between the LWD2 and the upper or lower reservoir boundary is half of the reservoir thickness, which is H1 plus H2. Let's take a deeper dive in the selection of model algorithms. The paper emphasizes the potential of machine learning in interpreting reservoir characteristics during drilling and highlights that the effectiveness of algorithms depends on factors such as sample data quantity and feature parameter types. For D-MP-VRB prediction, the paper selects algorithms including 1 versus 1 support vector machines, random forest neural networks, and extreme gradient boosting trees, beginning with 1 versus 1 support vector machines. Support vector machines are based on the concept of an optimal classification surface, especially for linearly separable cases, aiming to accurately separate two sample types while maximizing classification intervals. Originally designed for binary classification, used when encountering multi-classification problems. Key parameters for establishing prediction model with it include C and gamma. C represents the penalty coefficient, while gamma represents kernel function, which equals 1 divided by standard deviation squared. Kernel functions like polynomial, Gaussian, and linear are considered, choosing Gaussian for its flexibility. Gaussian function kx1, x2 equal exponential of the norm of x1 minus x2 squared divided by 2 times sigma squared. Optimal parameters are determined through grid search and k-fold cross-validation. Next, we delve into the second algorithm, random forest. In the 1980s, Bremen introduced the classification tree algorithm, He later integrated classification trees into random forest in 2001, marking a significant development in ensemble learning techniques. RF builds upon the bagging concept, using the classification and regression tree. It selects an optimal feature subset to partition decision tree subtrees, thus enhancing generalization ability. RF is efficient in classifying or regressing data and reducing computation time. It is robust to missing data and unbalanced datasets, with strong processing capabilities for high-dimensional data, leading to high calculation accuracy. Trained RF models exhibit low variance and strong generalization, with highly parallelized training processes for faster speed. Key parameters for establishing the D-MP-VRB prediction model with RF include N estimators, determining the number of trees in the forest, and max features, specifying the maximum number of features considered for splitting to balance variance and bias. Moving on, let's explore the next algorithm. Neural networks represent mathematical or computational models functioning as nonlinear and adaptive information processing systems. They consist of interconnected nodes forming multilayer nonlinear functions, creating complex and adaptive models. The critical component of neural networks is the activation function. This paper adopts the sequential model for constructing highly complex networks with careful selection of activation functions for input, hidden, and output layers. Additionally, setting a reasonable number of iteration rounds if the number of iteration rounds is too small so the model underfit the data. On the other hand, excessive number of iteration rounds lead the model overfit the data. The most significant algorithm, extreme gradient boosting, is a boosting algorithm that integrates multiple tree models into a robust classifier. During sample prediction, each tree generates a score, and the predicted value is the sum of all scores. It offers fine control over model complexity, supporting parallelization for faster computation. In establishing the prediction model, there are three key parameters prioritized: number of decision trees, maximum tree depth, and step size for weight updates, which consider as learning rate. Let's now turn our attention to calculation of distance between the bit and the vertical reservoir boundary. As we mentioned before what H1, H2, H3 mean, now we add another one which is H4, and it is the distance between the bit and the lower boundary of the reservoir. And we should know that symbol of zero length is S. The angle between the well trajectory and the horizontal direction, which is alpha equal by divided by 2 minus theta, which is well inclination, if H1 less than H2, indicating that the upper boundary of the reservoir is closer to the LWD2 than the lower boundary. The D-MP-VRB prediction model is utilized to predict H3 equals H1 minus zero length times sine of alpha minus beta, which is formation dip equals H1 minus zero length times cosine of theta plus beta. To solidify our understanding of theoretical concepts, we'll explore practical applications in our next episode, delving into real-world case study and validation results. Don't miss out on our next episode. Your insights matter. Share your thoughts in the comments below, tag a colleague who might benefit from this video, and follow my LinkedIn profile for more updates. Thank you for joining us on this enlightening journey.